So we can look at bivariate correlation in terms of graphs. However, we can also look at the data in terms of statistics. The most commonly used correlation statistic is Pearson's R, also known as Pearson's product moment correlation. Now, the correlation coefficient has a range of possible values from -1 through to 0 to +1. The number indicates the magnitude or strength of the relationship, from 0 for no relationship at all through to 1 for a perfect relationship. Now, the sign that indicates the direction of the relationship. A positive number indicates that the variables covary in the same direction. So in other words, they're positively related. A negative or a minus sign indicates a negative correlation, where the variables covary in opposite directions. So we have a correlation coefficient of the relationship between two variables, and we know that the higher the number, the higher the correlation, regardless of its sign. In other words, the stronger the relationship. But how can we interpret it and make it more meaningful indicator of the relationship? Perhaps the easiest way, but not the most informative, is to interpret the value of the correlation coefficient by eyeballing it and using the information here. So with a correlation of 0.4, you could safely say that there's a moderate relationship between the variables. Now, this eyeball method and checking it up against those set of numbers that I've just put up, that's acceptable. It's perfectly acceptable for a quick assessment of the strength of the relationship between the variables. But it's still a subjective judgment of what is strong or weak. What we'd like to know is a more precise method, which is what we'll look at now. A much more precise way to interpret the correlation coefficient is with the R squared. R squared indicates the proportion of variance in one variable that's explained, or more precisely predicted, by the other variable. Now, earlier in the lecture, when I talked about positive correlation, I gave an example of IQ and exam performance. If we correlated IQ with exam performance for people, we would find that the correlation to be moderately strong. In other words, their correlation would be about 0.5. The R squared would be 0.25 or 25%. And we get that by timesing 0.5 by 0.5. So this means that all of the variation in exam scores, from flunking to getting an HD, 25% is accounted for by the variance in IQ scores. The rest of the variance in exam scores, so in other words 75% of the variance that's not explained, for good or for ill, may include things like how you're feeling, your health, new relationships, your motivation to study, attendance at lectures, and your financial situation, and so forth. So this common variance is often illustrated with overlapping circles, each which represents the total variance of one circle. The unshaded proportions or portions of each circle represent those proportions of each variable that are unrelated and unexplained by the other. So if you take the scores that you may have got in math and English at school, you would probably find across a reasonable sample that the correlation is closer to 0.8 or 0.9. For those that do well or poorly in math, tend to, for the same reasons, they do well or poorly in English as well. So this is because how well they do may be related to their parents' interest in their schoolwork, how much time they spend studying, how motivated you were to do well, and so forth, which are related to both English and maths performance. So if we find, let's say we find a correlation of 0.8, then we can say that 64% of the variability in maths scores explains the variability in English scores. The more that two variables share in common, the more information about performance in one score can be explained by the other. Now, I'll talk more about how to use the Pearson correlation coefficient and the R squared in this lecture and later lectures.